It's a pleasure for me to be here today and give a talk. Dario, thanks a lot for the invitation and also thanks a lot for hosting me here. I will talk today about QoE-Aware service and network management for video streaming, which is, let's say, one of the research topics we are strongly involved currently. You also see it here with the number of names which are on the slide. So I present work from me and some of my colleagues. Before we start, maybe some small introduction. Who am I, where I'm coming from? My name is Thomas Zinner, and I'm a research group leader at the Chair of Communication Networks at the University of Wurzburg. My main topics, which I'm currently involved in, is our software-defined networking, network function virtualization, and QoE-Aware network management. First question, of course, would be, where is Wurzburg? Wurzburg is located, I would say, in the middle of Germany. You can reach it. You can reach Paris within less than 6 hours by train, which was quite nice. So you don't have to go for plane, etc. Wurzburg is very famous to some of very old buildings. You see here the Wurzburg residence, which was also, I would say, it was built after Versailles by the archbishops. And you also have a very old university. It was founded in 1402. And we still have very old buildings, but I would say the computer science is not located in these old buildings. It's located in a specific campus on top of the hill, which was quite built. It was built in the 60s, so it's quite new. And here you see also the Institute of Computer Science. That's where I'm working, where I'm located, which is one of these newer buildings. And if you have the right atmosphere, it doesn't look so, or it looks quite pretty nice. The Chair of Communication Networks currently hosts 16 PhD students and postdocs. Professor Tranchia is the head. We have a honorary professor, Hadal Benes, and 3 group leaders. That's me here, that's Florian Wamser, some of you might know him, and also Matthias Hirt. And we're supervising the PhD students. Our research areas, we come more from the methodological side. What we are doing is we are doing performance evaluation, performance analysis, and this includes, of course, measurements, testbeds, proof of concept implementations, simulations, but also, I would say, more generic things like queuing theory. So Jim Roberts knows very well about queuing theory. I'm not sure how many of you already applied, let's say, Markov chain or all these things to problems. I think some of you were working maybe also on spatial geometry, etc. So we are trying to find a good combination, I would say, about applied research and also more generic research. And we are applying it to several research topics, and these are future internet applications, upcoming video streaming applications like Dash, for instance, software-defined networking and cloud networks, to QE modeling and resource management. So that means we are really doing QE modeling. That means, we will see that later also, we are interacting with real users, doing QE service and trying to find relations between technical parameters, technical disruptions, and user expectations, user reactions, which is quite challenging. And last but not least, we are also doing network dynamics and controls. This really goes in the direction of complex networks, social networks, modeling of social networks, and then also bringing this back to communication networks by the interaction between social networks and communication networks. These research topics are split over the 3 research groups, which of course also have some overlap. So here on top, that's the next generation networking group, the group I'm heading, where we're doing also stuff on softwareized networks, how softwareized networks change the telco landscape, the networking landscape, and with particular focus on performance evaluation of these technologies. We are working on controller placement stuff, network monitoring, and also then again, network application interaction. So we are always trying to get a more holistic view on the problems, not only by investigating only quality of service, but also how quality of service impacts the applications running on top on the network. And Florian is doing the same with more emphasis on cloud networks. And Matthias is working, I would say, on this layer above, something like layer 8, where he's doing more involved in the social network stuff, and also in things like crowdsourcing and using crowdsourcing to do QoE modeling. That means how to implement user service and how to deploy user services, for instance, via the internet, so that many people can access them and give back feedback for specific stimuli, for instance, for different stalling patterns when the video stops, etc. Oh, sorry, this direction. Good. For the agenda for today, I was hoping to have maybe some more interactive talk where we can also discuss about the things which I present. I have 4 topics. An introduction to quality of experience in general. What is it? What do we mean when we say quality of experience? How does it differ to quality of service? Then I would go into detail a bit into QoE monitoring for HTTP adaptive video streaming. We can go also for some QoE modeling and analysis of HTTP adaptive video streaming using discrete time analysis. And can also investigate application network interaction, which means a better cooperation between applications and networks. But I would just make it also up to you. So I would say, are there any preferences from your side? Any specific interest? So I would just start and let's see. If you're not interested anymore, just let me know, then we can skip some slides, etc. But of course, I'm trying to make a vivid public presentation. So who of you has already heard about public quality of experience? I know Diego is working on it, Jim, of course. So only a couple. Let us start with some basic discussions about today's internet and also about today's application. Everybody of us is using applications like YouTube, Facebook, Wikipedia, Skype, WhatsApp, etc. So we have a very large application landscape also with heterogeneous demands. Skype poses completely different demands to the networks, and YouTube is doing that, than things like WhatsApp are doing this. And the interesting thing is that also we have all these changes at the edge and on application level with new applications coming into the networking ecosystem. The network itself is evolving very, very slow. Most of them, or these applications, are still delivered on a best effort basis and are mostly, despite Skype, despite also now YouTube and Dash video streaming, they are still on application and network agnostic. So it's just transmitting the data, particularly the network transmits this data without taking into account which application is running on top of it. Okay, if we just think about if we have typical multi-application scenarios where different applications are sharing a bottleneck link, that means that they are all running or all transmitting the data via this link. That means YouTube, voice over IP, online office, something like a thin client architecture, for instance, or software distribution are using the same network, and they all have different demands. Yeah, YouTube video streaming should not stall. Voice over IP requires regular or constant bitrate available. Same holds for online office, but which might use another transport protocol, etc. And software distributions are just a file download. And if they are using the same bottleneck link, it might end up in problems. Just if we break it down to YouTube video and software distributions, we all know both applications are using TCP. So in the end, we end up in a fair TCP, a fair share of resources by TCP among both of these applications, which might be enough for the software distribution, for the file download, but it might end up that our YouTube video clip stops because there are not enough resources available. And what we now need is, we somehow need to get away from this agnostic transport of data, and we have to do it with respect to the application, and also it's what we call QoE-Aware resource management with respect on how this application affects the user experience. So just let me break down this example. We have this here, we have just an exemplary graph just explaining the behavior if we have network agnostic data transport. That means we have the TCP fair share. So that means our data and our YouTube application get the same resources, get the same bandwidth, and this might end in problems for YouTube because it's not enough bandwidth available to provide the necessary video bit rate. And we all know what will happen, the video will stop. We all know this famous wheel or circle when not enough data are available to continue the video streaming. But in the end, what we really want to have is, we want to have a full video buffer so that always enough video is available at the client to guarantee a continuous playback. And how can we achieve that? Of course, we somehow need this information that not enough data or not enough resources are available at the client, that the video might stall, and then we somehow can prioritize this in the network so that additional resources are available. That's what we call application-aware networking. Or, on the other hand, what we also could do is that the application detects this problem that the buffer might, or that we might end up in a buffer underrun, and adjusts its demands. So that means that it reduces the bit rate it needs. That's what we call network-aware application design. And this is a very general terms. So if we bring this now down to quality of service and quality of experience, just here I have this typical ITU recommendation which defines quality of service as the totality of characteristics of a telecommunications service that be on its availability to satisfy stated and implied needs of the user of the service. So in the end, that means we have here an objective, measurable view. QoS focuses on the technical parameters. But on the other side, if we take a closer look at QoE, and that's a definition by Consequently, is that the QoE is a degree of delight or annoyance of the user of an application or service. It results from the fulfillment of his or her expectations with respect to the utility and or enjoyment of the application or service in the light of the user's personality and current state. So, and you see this is completely different. Technical parameters, we can monitor, it's not a problem. But now here we get really in the user and also how different or how user or the heterogeneity of the users. Everybody of us has different expectations. Also our expectations change. If I'm currently in a run or in a rush because I want to catch the next train and I'm trying to figure out when my train goes and if it might have some minutes of delay, I will behave a network delay or an application delay in a different way when I'm just sitting in my office and browsing on a news page site, etc. So what you see here in this context of communication services, QoE is influenced by many other factors besides the network. It includes the service, the content, network, device, application, and also the context of use. And of course, this is now a very holistic view, which of course, if we want to break it down or if we want to use it, makes it really, really hard because we cannot manage the network for every user individually. But that's a bit the trade-off. That's what QoE is. And the question is now, how can we get, or which are the important parts for specific applications which we have to take into account? So coming from this holistic view, we now can then break it down to key performance and key quality indicators, which we then might try to manage again. So this is again a comparison between QoS versus QoE, where we just have the different scope, focus, and also the method of both technologies. So it's just part of the slides. I think Dario will distribute the slides after my talk. So if you just go through it, you can just go through them afterwards. So if you want to do now a QoE assessment, that means we somehow must understand the fundamental relationship between the technical system and the user perception. And this always ends up in the typical questions: what kind of application do I have? What are the key performance influence factors on this application? If I have some video on demand video streaming, of course it's bandwidth. If I have something like a voice audio call, it's not necessarily only bandwidth anymore, but then we also have the delays which we have to take into account, etc. So we need to come up, or we have to define what we really need to measure, and we somehow have to find out how we can map this, or how the relation between these measurable parameters and the user perceived quality is. And for that, of course, a huge number of different assessment methods exists. On the one hand side, it's good to do your QoE assessment in a lab, because there you have a reproducible environment. You can think about the distance, or you can also control the distance of the viewer and maybe the TV. You can think about if the light is turned on, etc., and all these things. So I can do my QoE assessment in a very controllable environment, but in the end, the user will mostly watch video at home, where he might have completely a different surrounding, etc. So the question is always, if I do this QoE assessment, how do I do it, where do I do it, etc. And there are tons of paper discussing the pros and cons of these different possibilities. But in the end, we somehow use subjective methods to get the user into the boat and to try to find some way of a mapping function between technical parameters and how the user experiences. And what we want to do is, of course, we want to understand root causes of unsatisfactory or degraded QoE, because we want to identify when is the user having a bad quality, when do I have to change something in the network or in my technical system. And that's where, as already outlined, at our department we have a number of different research challenges in this direction. So it really starts with finding models for Dash, or understanding better the impact of adaptive video streaming on the user perception, and goes down really to what I will later also show, how can we, or how are we trying to really monitor quality of experience of a user watching YouTube. What I also would like to explain to you is, as already outlined, there are somehow or very generic relationships, and that's quite interesting. There are generic relationships for specific applications between QoS and the QoE. This is a paper from 2010 from Tobias Hosfeld, Markus Fiedler, and Vogt-Rangier, and it's called the IQX hypothesis. And the hypothesis is that with increasing QoS disturbance, something like, for instance, packet loss or increasing delays, you have a negative exponential decrease of the user experience. And this is very interesting. So that means you decrease, you increase your disturbance, and there's a specific level when it affects the user, and then your quality, or the QoE, drops very, very fast. And while increasing the disturbance, it decreases slower. So that means if you have a very, very high QoE and some small disturbance, that might already impact the user very strong. And for instance, it's just a typical example, or an example, which is also part of this paper, where they investigated voice over IP services. And there, they increased the packet loss, and they investigated the impact on the MOS value. It means on the user perception. And as you see here, this goes down in this negative exponential shape, which they also use to fit it. So what we end up is we get a mapping function for this service where we see the impact of the packet loss, that means on the QoS parameter, on the QoE. And the interesting thing is that this not only holds for audio or for voice over IP, but also for other services. What we here have is, for instance, the impact of stalling for YouTube video streaming. That means what you see here on the x-axis is the total stalling time, and what we see here is also the impact on the quality of service. And of course, the more stalling I have, the less bandwidth is available for my service. And what we see here also are other impact factors on the quality of experience. So what we are investing here is we have a specific stalling length, and we either have here on this curve, we see a high frequency of stallings with a duration of 1 second. So that means here, if I have a total stalling time of 10 seconds, that means I have 10 times 1 second of stalling, versus here I have 1 time 10 seconds of stalling. And the interesting thing is, here again, we again have this exponential shape of the curves, but we have different parameters. What we see here is that users, or that a higher frequency of small stalling duration has a higher impact on the user than a small frequency of longer stalling durations. Yes?
The red curve is 1 second times 10, and then the other one is 1 time 10 seconds.
Yeah.
Okay.
So that's what you have here. It's a fixed length, 1 second, and then n times. So you also found here always the references to the papers, if you're interested. Another more generic thing is what we call the provisioning delivery hysteresis, because after some time, after investigating different applications, we saw that there are different possibilities how you can adjust to a bottleneck link. If I just send in too much traffic, I will have packet loss. And that disturbs my service in an uncontrollable way. Yeah, sometimes more important information are lost, sometimes less important information are lost. On the other hand, and this is now that was comes to this adaptive streaming idea, is if I adjust my video quality in a graceful manner by just reducing the bit rate to the bottleneck, I will not have packet loss. But I will have a lower quality of my video clip. And that's what you see here. I have here, I call it the good-put ratio. So let's say in the end, the application layer perceived throughput, and that can either be reduced by adjusting the video bit rate or by having packet loss. So in the end, it's just very, very simple computation. If I have some packet loss, my overall throughput is reduced by this amount of packet loss. And here we have this controllable quality distortion by adjusting the video quality. And we see here that if I have the whole good-put ratio of 1 means full video quality, full MOS value, best user experience. And if I reduce the video quality, I reduce the user perceived quality very, very slowly until a certain point where it then drops faster. So in the end, this is due to, I don't know if anybody of you is familiar with information theory and coding theory. In the end, this is the impact of the rate distortion curve, what you're seeing here. It's typical behavior. But what we see here is now, what is happening if I get packet loss? If I get some packet loss of 1 or 2%, I also reduce the application layer perceived throughput because some parts of the video are missing, but the quality drops much faster. So we get again this very strong reduction. And these are, let's say, these 2 branches of the provisioning delivery hysteresis which can happen. I can either have video stalling because there is not enough bandwidth available, then I end up also in this branch. The quality drops very, very fast. Or I can just reduce my quality. And that is what techniques like Dash are doing, adaptive video streaming. They just try to find always the best fitting quality for the available resources of the network. And that means you are, oh, pardon me, we are here on this branch. So what I now already brought in, of course.
I'm sorry, I'm just trying to understand. So how you're going to do, so in practice, as you're saying, you might have some stalling and some quality reduction. It depends on how the algorithms are adjusting. But how do you go, I guess, from one side to the other? So the models, do they take into account both parameters at the same time?
In the end, you have to, and that's what is currently also happening, or I will come to this later. Yes, you have to, of course, you have to take this into account, but, or at least you have to take this into account, but on the other hand, that also means for you, if you are running in such a disturbance, if you're running in stalling, if you're running in packet loss, you have a huge problem. And as long as you just have quality switches, things are not so worse at all. And that's also what we see, and also what, let's say, our current research indicates. We'll come to that later. But you brought in a very, very interesting point. How can I switch between those both branches? Because what we now have here is 2 different loops somehow in the end. And that's the next one. We have a service running on top of the internet, or on top of the network. We have YouTube running, and they have their own adaptation cycle somehow. The service has its own possibility to adapt. So he just is probing the network in any way in case of our video streaming application. They are investigating the current buffer level, and based on this buffer level and maybe also on some way of network monitoring, they are deciding if they have to switch or if they can stay on the current level, or maybe also if they increase the quality level to provide a better service to the user. On the other hand, we have something similar in the network, or we might have something similar in the network, where we have monitoring of the available resources, and maybe also doing then some resource allocation decision. Maybe also to identify specific services and provide additional resources for them. And that's also where this direction also goes, maybe also being able in the network to estimate the quality of the service and then taking this into this decision loop. But what I want to say is that we have 2 different loops which are not connected. We have a control loop on the application, and we might also have a control loop in the network, which might be also working on other input parameters, particularly, for instance, only on packet loss or something like that, and trying then to do some flow rerouting or some prioritization, etc. And the interesting thing is now to bring in this QoE view into it. The question is now, how can we monitor QoE? And as you have already seen, we have to think about how can we monitor it on 2 different layers. How can we monitor it on the application, on the service layer? That means maybe either it's a server or it's a client directly. And that's usually, I would say, that's more easy. You only have to know that if you are an application provider, you know what the user is interested in. Yeah, in case of our YouTube application, that means I have to take care about that my video buffer does not run empty, because then the video will stall. And if I have done this, that's pretty good. The next thing would be to try to provide the best video quality, which is currently possible. And then I'm done. On the other hand, doing this in the network is quite more complex. So you have to collect data via probes, you have to get all your monitoring data. You might even need flow-specific or application-specific occasion which you take into account. And based on this, you need a methodology to somehow bring this information which you have to QoE. We started to do that. We implemented even a video buffer estimator for YouTube on a home router, which gave us a possibility just to estimate what is the current buffer level. It was running quite well, and we could also then adjust our network control. But then we ran into an interesting problem. A couple of months later, YouTube turned on encryption. So now encryption is on, you have problems to get all this information which you had before. So what's now going on is, okay, this is getting much more complex, but we still somehow need this information. And at least Diego is working on this, trying to get this into account, or to get this solved with machine learning approaches, for instance. Yeah?
Have you seen last year's Internet Measurement Conference paper by Telefonica folks? They have something for YouTube where they're doing exactly this. That they are looking to the encrypted traffic in their mobile. Like they're looking to a proxy, but it's a similar kind of data. And they're using machine learning to infer the QoE from the encrypted traffic.
Just to get this information. Yeah. So that's how it's currently done, but it was really, at least also for our approach, a showstopper. Okay, what I already mentioned, which I want to just define now a bit more in detail, is the evolution of the video streaming mechanisms. So if you think 10 years ago, when you think of YouTube video streaming, you only had one quality, or at least you were not able to switch between these qualities. And you were just watching one quality, and either you had enough resources, or if your network resources changed over the time, you had stalling. But in 2007, people came up, the first idea was this HAS concept, this adaptive streaming concept, was to allow the service to adjust the quality, and also the interesting thing was to move all this intelligence, how to do this adjustment directly to the client. So the client was able, or was the one to decide about the quality he wanted. And to do that, the video was broken down into segments, and the segments were encoded in different quality levels, and encoded, and during the video streaming, the client could choose could choose for each segment in which quality he wants to download it. So it brought us in, of course, additional control traffic, and also this concept of just breaking the video down resulted also in additional overhead, additional coding overhead, but it gave us this flexibility to adjust the quality and avoid stalling. So HTTP, adaptive video streaming, is usually transmitted via TCP/IP. That means we have a guaranteed delivery, we have also a guaranteed quality, but what may happen is that we get stalling. On the other hand, what's currently also used for video streaming, more in the real-time context, is WebRTC video streaming, which is then transmitted via UDP, and where you then have as distortion artifacts, etc., and packet loss. So these are the two ways, I would say, most of the video traffic is currently transmitted, and what we are focusing on, of course, is on HTTP adaptive video streaming, also in this talk. But of course, the ideas and also the concepts can, of course, be applied to other technologies like WebRTC. Okay, in the next steps, I want to discuss a bit more the QoE monitoring for HAS services. When we have adaptive streaming, we have a stateless server hosting the content. We have a manifest file which has to be downloaded in the beginning, which describes the available qualities and also the available segments, and which allows the client to get the desired segment with the desired quality using a HTTP GET. And the one, as already outlined, who is responsible for or what to download is the client. And he requests the chunks via HTTP, which allows us to use the available caching architecture, which also results in that we do not have any problems with nuts, etc., because everything is done via HTTP via port 80. Okay, he decides which quality to download based on his current state. So that means he takes into account things like the buffer state. He also might do additional measurements. And the interesting thing is this selection, what to select next. That's, I would say, or it was part of extensive research. So I don't know how many different heuristics have been proposed or different ways to select the quality since something like 2012 and 2013. I'm aware of at least more than 10 heuristics or 10 ideas how to do this download. Some of them are commercially deployed, for instance by Netflix. Others are only part of research papers, etc. But I would say what was in previous times the research for the next best TCP algorithm is currently the quest for the next best dash heuristic. Based on this, or based on the decision, different segments are downloaded and a different quality is available at the client. The slides are. Dario, you take care about circling the slides afterwards, or? Okay. The questions which are now arising are, of course, how shall I encode my video clip? How many different quality levels do I have to provide? How do I do the quality adaptation? Am I using different resolutions? Can I change the frame rate? Can I do different spatial resolutions, different quality levels, etc.? Or image quality? These are research questions which still, I would say, are not solved. And as already outlined, what is currently also missing is a holistic model describing the quality of experience for HTTP adaptive video streaming. As already outlined, in general, stallings have a much higher impact than quality switches. But that does not mean that we can get completely rid of quality switches. There are also other things which have to be taken into account, like the amplitude of the switches. Am I switching from a very, very good quality to a very low quality? Then the user will perceive this quality switch. And it will have an impact on his quality of experience. If I'm only switching between quality level 5 and quality level 4, he might even not perceive this. These are all impact factors, and we're also active research is currently going on, where we were also involved. So there's also now a standard or a standardized model for this. But I think this question or the question is also where to apply this model to. If I'm doing, or if I'm sitting at home, I'm watching a movie, delays and also quality switches might have a completely different impact on me than if I'm doing something like channel zapping or going on YouTube, switching between video clips, searching a specific video clip. If I'm sitting at home, initial delays might be something which I tolerate. If I'm switching between video clips because I'm looking for a specific video clip, initial delays might have a high impact on my experience of the service. So it always depends on the specific use case, the specific scenario, what you are in, what are the dominant QoE influence factors. That's also something which you have to take into account. Okay, how is HTTP adaptive video streaming working from a network perspective? Well, in the beginning we have the TCP handshake, we have this MPD file which is downloaded, and then the client can start to download the quality segments. So you might request segment, the first segment in a specific quality, which is then downloaded. After it's downloaded, it's available at the video client. That means we have our first video segment. That means we have a specific video buffer available. The video starts to playback. The video buffer starts to drain. And of course, we know, or our player knows, or heuristic, oh, we need a new segment. So he requests the next segment in a specific quality, which is then downloaded again and hopefully arrives before our first segment is played back. This results in an increase of the playback buffer again, which of course depletes until our next segment arrives. So what you see here is the impact of TCP connection, here of our heuristic, and here in the end the impact on the video buffer which goes up and down. Quality is not included in this picture. I think, Jim, you know this kind of diagram, because it again goes in the direction of time discrete analysis, which I will discuss later. If now a segment of too high quality is requested and it's not arriving early enough to be played back before the video buffer runs empty, we end up installing. So here we have a stalling, and the video buffer is again filled after a new segment has arrived. So that's the typical behavior, and usually, at least the heuristic tries to avoid these video stallings. So what we have usually, or what we have if our application is doing well, we have in the beginning a ramp-up phase where the player requests quality or segments very fast to get to a certain video buffer level, and then it tries to stay at this buffer level. So that means you're trying to get 30 or 40 seconds of video buffer, and then you're trying to oscillate or to stay around this value. Usually you do not download more segments, because as service provider you cannot be sure that the user stops to watch the video clip, and you do not want to waste resources by providing more content or much more content than will be used. So you have in the beginning this buffer filling phase, then we have the steady state, and when the video clip comes to an end, we have this buffer depleting phase where no further segments are downloaded. Usually, or if everything goes right, the buffer level or this behavior should look something like that. So how can we now do QoE monitoring for such a service? We can do this on application layer by in-service monitoring. And the interesting thing is YouTube is doing something like that. You have here their specific tools which you can access also. And you see what they are monitoring. They are monitoring frames per second, which are displayed at the user device. They are also monitoring the download, etc. And this allows them to also monitor the quality of experience-related factors. And if they see the problems are happening, they can adapt the service. What you also can do, or at least what my colleagues at the University of Wurzburg are currently doing or already did, is they implemented an additional software. They implemented their own Android app. They call it YOMO, the YouTube Monitor. And this is a customized app which allows you to gather additional information and maybe provide information from this application to a network device. Because the important thing, if you want to do QoE-Aware network management, is that you need somehow information and you somehow need to get them. And this approach is now going away from this. We are trying to do machine learning based techniques or methods based on our traffic. It's about why not going towards providing an application which we trust and which provides us information which we can use. And just some more information about this application. It's available also via the Google App Store. And it's a mobile application which uses or which you will not, which can display the YouTube mobile website. And it also uses a HTML5 video player. And it's a completely, fully functional YouTube application, including all the features of YouTube. Yeah, in the end, when you are using it, after starting it, you will not see a difference. But it does immersive monitoring. We get additional information. We get video bitrate, we get signal strengths. In the end, we also ask the user about his experience with the YouTube application, and we can gather this information at a central server and use it there. Additional things like device characteristics, also user interactions, that are all information which we can gather with this application. We can also see if he pushes the pause button, etc. And all this information are gathered. And currently what they are working on is to get users using this application, also doing the ratings, and then providing a map with information about where your YouTube streaming experience is good or not. So just for the community, the easy question, I want to watch a YouTube video, where do I have to go? Where do I have enough network coverage to watch a video without having disturbances? It's a bit the idea currently of what they're working on.
Do you think it's relevant to do that on smartphones? I mean, given the size of the screen, etc., you might not get the same impact in, for instance, KT switches that you would get from someone watching Netflix on his 4K TV.
Well, in the end, the problem that you have is that even the YouTube smartphone app behaves different than the YouTube desktop app, etc. So what we what we saw is that you have to break it down to a device level. You cannot even say that the same application behaves similar on different devices, etc. So, and it was quite interesting. That one was the outcomes of this application. So, but yeah, you have to bring it down to device level.
So have you
application and device level
for Android, or have you also done it for PC
only
or?
We also, of course, we have a browser plugin for PC, where you also can get this information, etc. So we're also able to compare this, and that's when we just figured out that, which makes, of course, completely sense to treat a mobile where you do not know how the bandwidth or the available resources will evolve over time. You have to take it differently than a fixed network PC, etc. A networked PC. What we also did, it goes a bit more in this direction of your comment, is about this the packet inspection of service flows, where we try to get this information to estimate the quality of experience within the network. Because, of course, for that you do not have to write your own application, you do not have to deploy it, you do not have to take the user into account who has to install it, etc., which makes things a bit easier. But of course, it's much more inaccurate, and what was also really a problem which we saw, it's very inaccurate in case if the user starts to interact. If he starts jumping in the video clip, you have problems because you do not see that, or it's hard to get this information when you just investigate the network.
So in the case of encryption,
Yeah.
you can do this.
If you, in the case of encryption, you just can rely on machine learning. So many of these discussions were, what you also can do, of course, is if you have a proxy, which is, you can do a man in the middle. That's a possibility where they're also very experimenting with. But without man in the middle, you only can rely on machine learning currently. But well, it's only for. Of course, we have done this for YouTube, but you can also bring this methodology to other services. You might also bring this for specific services which are within an enterprise network, etc. And then you might not have this encryption problem, or you might be able to be the man in the middle without having privacy issues, etc. But so there's also work available where they then adjusted it to a cellular network where this was used. And using passive probing. And they now also changed all these things, of course, to machine learning to get this information about the application quality and to use it to estimate the user perceived quality. So, but, well, this is the stuff discussing this towards network monitoring. The problem is now that the time is running and I only have made half of my talk. So now we are at this. What are you interested in? Modeling or some more interaction between application networks? I have to choose, okay. Then I do not want to switch now by fast going forward. Just go to some modeling. Because, well, you know, university, you already have, or you know this picture. You know this going up and down. And the interesting thing what we have here is, every time we get a segment, our video buffer increases for a specific amount of time. This can be a fixed segment size. It can also be a variable segment size. For most HTTP adaptive streaming deployments, it's a fixed segment size, something like 2 or 4 seconds. And then what we have here is, we have inter-arrivals of requests. Yeah, my segment, I can monitor this segment inter-arrival time. Here. It's also here. So I can bring this down to stochastic processes. I can, to a certain extent, model my video buffer as a queue. And that's an interesting thing now. For a video buffer, it's always good if this queue is full. Completely wise, but typically in networking, we try to avoid the queues or it's always good if it's not so full. In our case here now, if my video buffer is full, everything is good because then my video will be played back. And if my video buffer runs empty, I have a problem. So we can bring this down to segment inter-arrival times. We can bring this down to the segment service or the segment play time. And every time a new segment comes in, my buffer, my queue goes up, my buffer goes up, and it's slowly depleting because I'm playing back the video clip. So, what we did is now we brought this down to a discrete time analysis, where we just said we have a GI1 buffer with a PQ policy. PQ in our example here means that we have here a hysteresis. We go up with the video buffer time. Here we have the stalling when it goes below. And if we get above Q, we stop. the requesting of segments until we drop under another threshold, that's this P threshold, and if we are below the threshold, we again start to request. So this is a typical behavior, particularly for mobile video streaming, because here, what you are getting if you only have one threshold, is that you're always circling or around the threshold. And that means if you have a mobile phone, that means that you will always requesting segments. So you don't have large gaps between these requests, which means that your network interface is continuously consuming energy. And if we have these gaps, there are also these possibilities that the network interface is going to sleep mode for a certain time, and so you can reduce the energy consumption. That's why we also brought this into this model. And what we are now doing is we're bringing this down to discrete time analysis. So in the end, what we are doing is we have the inter-arrival time, we have the service time, and we are just always computing this video buffer in an iterative manner. So this is, I don't know if you are aware of discrete time analysis or how many of you. In the end, it's a numerical solution. It's just, you have a fixed point approach, you have an iterative, you're using a power method, by just finding the fixed point, which is a steady state of your video buffer distribution based on your inter-arrival times and based on your service times. So you have distributions and you're doing convolutions. That's what you are seeing here. The only thing which is a bit more of interesting is that we have here different operators which take care about in which state we are currently and if we are now already, or if we are still requesting, or if we have to wait until we fall under a certain threshold. So I do not want to discuss these details with you. If you're interested, we can discuss after my talk about this. But the cool thing is now that we can compute the video buffer and we also can compute it in a time-dependent manner. So we really can say, after the next segment is coming, how is my video buffer distribution? So if you're just starting with a specific state, let's say we start here. In the beginning, we say it's empty. Then we download a segment. That means it goes up to 2 seconds or to 4 seconds. And now it depletes until the next segment arrives. And then I have some segment inter-arrival time, some arbitrary distribution with some arbitrary mean. And either it arrives early enough or not. If it's not, if it arrives too late, we have stalling, etc. And this can be computed. And we now can compute this in this iterative approach. It goes for the after 3 segments, we have this buffer filling distribution. The red one is an artificial distribution, which it's due to how we are doing this computation. We might end up in a negative buffer. A negative buffer, of course, is not possible. It's only possible here as interim state. The cool thing is that we here have the possibility that we have a video stalling. So more important is the red part here, which is the video buffer distribution after the arrival of my third segment without negative buffer. And what you see here is now that this distribution just increases until it reaches a steady state. And that means we are able, for specific inter-arrival times and specific service distributions, to compute the steady state of my video buffer. And that's now quite nice, because now we can play with it. We can just think about, okay, which network conditions result in which inter-arrival times, and I just really can compute for a more variable network, the video buffer distribution, and I can compute it for a constant or stable network. So I can just see how this affects my video buffer. And I have several parameters. I have the over-provisioning factor A, the average bandwidth, divided by the average video bitrate. And we'll see an interesting result later. But usually, if you want to have a stable video playback, you need more bandwidth on average than the video bitrate is, because video bitrate is variable. It's varying, and to compensate this variation, you need 10, 20, 30% of additional bandwidth on average. Otherwise, you will experience stallings. We have the coefficient of variation of the bandwidth, and we can compute several metrics like the stalling probability, the rate of stalling events, the stalling duration, and also the wasted bandwidth in case of termination by the user. And what you have here is just a fixed over-provisioning factor. That means, on average, I have 1 to 2 times more bandwidth available than my average video bitrate is. We have here a variation of the network, and we just see how this affects my stalling duration probability. Of course, the higher the variation of the network, the higher the stalling probability. What we did is, we did, of course, measurements, just to see how good our model fits to reality. And what you just here see is different over-provisioning factors for different variations and the corresponding measurements. So you see here, the bars are our model. The dots with the confidence intervals are our measurements. And you see we have quite a nice fit. And a very interesting thing what you see here is that, of course, depending on the variation of the network, we need a specific over-provisioning factor to assure or to have no stalling. So we have here the average stalling probability, and here's the average stalling duration. So that's quite cool, because we now have a model which we can use to investigate these different impact factors and how they affect our system. We can also use specific mapping functions. So this is, in fact, the stalling mapping function you saw for YouTube. And based on this, we can also compute the QoE. So we can just say, OK, if we only have stalling as impact factor, no quality switches, etc., this is a good fit for that. How does it really affect my system? And last but not least, we can also use it to investigate the impact of this buffering threshold. How shall we set this P and this Q? How does it make sense? And maybe also, what are good parameters for different network variations? If I have a stable network conditions, I can set this parameters differently than I have a variation. Because if I have a variation, I might go to a higher buffer to be able to compensate less network bandwidth for a longer time, for instance. These are all things which we can do now with this model. Good. Said enough. I suppose sorry for this, since it took a bit longer. This is the part which I would skip, and I would just come to the conclusion slide. My talk covered a bit quality of service and objective performance metrics, and also the relationship between quality of service and quality of experience. I explained some different possibilities to do quality of experience monitoring on network layer and also on application layer. And I discussed also with you how we can model applications like adaptive video streaming using discrete time analysis. And I also showed a bit how this can be useful to optimize the service with respect to parameters like network variation and also service-related parameters. I think, or just as famous last sentence, what you have seen is we have impact factors on service level. We have impact factors also on network level. And each part can try to optimize quality of experience using different possibilities, but in fact, if they are doing this without interacting with each other, they will be able to improve the quality of experience to a certain extent, but that can be, but if they interact, and that would have been the fourth part of my talk, they can improve the quality of experience to a much higher extent. And this is where also, at least at our department, our current research is focusing on how to better bring applications and networks together. But we will distribute the slides, and you can then take a look at it. So thanks a lot for the attention. I think this was...
Actually, in everything that at the very beginning you had a slide that said that it's entirely subjective. So I have not the same quality of experience as you have under the same conditions.
Yeah.
And then everything you do is actually averaged over the whole quantity of users.
Yeah.
Do you know of anyone, for instance, Google knows how I'm watching YouTube. He knows that maybe I'd rather wait at the beginning when someone else and have a better quality when someone else wants his video right now and he's going to quit if he just waits. Do you know if they're even trying to do some, let's say, very personal quality of experience optimization or not? Or are they just averaging?
I would say so. But what they can do, of course, is they can try to take preferences of you into account. I bet they are trying to cluster all the people to see who behave similarly, etc. to use this.
But this means
so
that
really
if I'm more patient than someone else, I might just get my video delayed and then the lower quality because that guy is more.
At least it would make sense, because it would optimize your quality of experience. Yeah, but that's a bit also this question: how much can we do on a micro level? How much can we only do on a macro level? And depending where you are, so of course, I would say also this is where at least what all these big data approaches at least promise us is to get it to break all these things down to a more individual level. We will see if this is doable.
One of your first slides was the case where YouTube was sharing bandwidth with downloads, but then you didn't speak about that. How does that work out if you start giving better quality to the YouTubes because you give them more bandwidth? What's TCP going to do for the download? Are they going to suffer? Or is that an optimal experience for the user always?
Well, it was a very, very, let's say, of course, a very, very simple example. We made measurements where we just prioritized YouTube when the video buffer was running down. So only for a shortened extent of time, we just prioritized it to ramp the buffer up, and then we reduced this prioritization, so had again a fair share. Of course, you have to take into account things like how is TCP reacting. You're reducing the overall efficiency for the sake of increasing the quality of experience for one of the applications. So in the end, of course, the download time is larger, but only to a certain extent. It was a couple of seconds more, but and what we have is that usually downloads are not that important. They are either done silently in the background.
There might be someone else who's got a Netflix while the YouTube's in progress. So if you're optimizing the YouTube, someone else is optimizing the Netflix.
Of course, if you have something like that, if you have such an application which is very sensitive, via to network disturbances and also to lower bandwidth allocations, that's something which you have to take into account.
But who and where? I mean, you said you're giving priority to the YouTube. Where?
Yeah.
In the network?
We had a network emulator running there. Yeah. The question is, of course, now where to do it.
Yeah.
Do I do it at the edge of the network? I cannot do this in the core of the network. It's definitely not possible. Yeah, but maybe I can do it at the edge.
At the edge, yeah.
Maybe I can do it also using technologies like, for instance, SDN, if it's possible. If you have something like this running, or if you have running this in a data center, that might be doable. That's completely with you. The question is always where to apply this. In our case, we also, we're using it, in the end, we're using it via a wireless access network. So we're able to do it directly at the wireless access point.
Just following up on what Jim was saying, one challenge is to really capture the priorities in general. So I really enjoyed the SICOM in Brazil, that Nick McKeon in Brazil, they had a paper of this idea of network cookie. It sort of goes towards what you're saying, but the user would decide.
Yeah.
So I could say, okay, now boost my YouTube.
Yeah.
And then that will send my ISP, and then the boosting will be done based on the user is in the loop. I don't know how they prioritize against multiple users, so Jim's question is still valid here.
Yeah.
But I think that's an interesting area in general, and like just capturing the priorities and then solving the conflicts that will arise from different users having different priorities seems to be a very hard problem.
That's a completely valid question, and that's also something which we are currently working towards. What we now want to get into account is, of course, multiple applications. Multiple applications also with different demands. And there all these questions arise. How do you get the user into the system? How can he participate? To which extent can I do that by not taking him into account, but just using some model? What is the problem I get when I do this? To which extent can I give him the possibility that he decides that I now, or even maybe also let him decide whether it's better for him to have quality switches instead of having delays, etc., or stallings, all these things. It's a good and it's a valid question, and I think there's still work to do in this direction, and providing him interfaces, charging it. I think the most important thing is really, just also to have this idea that I have to take him into account and I have to provide this information in a way that he understands it. Just.
And I think that you said something charging, like now on top of this, they're doing a zero rating, and so the QoE, when you're mixing with the costs, it's going to become another.
That's but these are the things which Peter Reichel is investigating, so he's working in this direction about how to it in. Well,
maybe since Thomas is going to be here for the afternoon, we can maybe call the talk. Thank the speaker again, and then if you're interested to follow up, he's going to be around.